So, like I said, so the theme of this chapter, obviously we're doing any sort of and every sort of calculation you could possibly do with the vector. Now, here's the deal. If you look at the formula sheet, we're pretty much doing everything on the front side except the very bottom one today. The math in all of this is super easy, and there's nothing too crazy time consuming. But I will preface it with there's a lot of, as you look at the sheet, formulas. So it's important that you read closely because some of the formulas are super similar, and make sure obviously you're using the correct one. You do get the formula sheet on next week's quiz, and you will get to use the formula sheet on the test. Because there's so many of them. I don't want you so worried about memorizing formulas. I want you to know how to use the formulas and do the calculations. That is what we're after. So one of the main formulas we're going to use in this section, and it comes up in another section when we do three-dimensional vectors, we're going to talk dot product. Dot product is used in a lot of the formulas on the sheet. Now, as you can see, of course, if you get into physics, you'll see dot product in there. Calculus, dot product comes up a lot in calculus, especially if you take Calc 3 ever in college, just for the record. I'm just going to show you how to do mostly the computation or the operations today. So, first off, this does not mean multiplication. We are used to the dot being multiplied. So just recognize you are not doing straight multiplication here. That dot in the vector world means dot product. So to do the dot product, pretty easy. You multiply the horizontal components together, and then you add to it the product of the vertical component. So it's not straight multiplication. And you will see in another chapter, chapter 10, dot product actually comes up when we talk about matrices, and we multiply matrices together. So looks crazy, but the math, super simple. Here we go. We're going to multiply the horizontal components, mental math, though. It's 3 times -4. And we are going to add to that, switch colors for drama, the product of the vertical. What's 2 times 5? 10. Total it up. Final answer. We're done. So see, math is super easy on these, okay? Same thing. You're just in the I and J. Same deal. Multiply the horizontal component first. So 2 times 5. And then we're going to do our vertical. Really a 1 there. 1 times -6. And, of course, add it together. Okay? Simple. Very simple. And you will see why we start with dot product. It is in some of these other formulas. Dot product, dot product, dot product, dot product. Thought I'd say it one more time there. Dot product. Now, some of the properties of dot product, simple stuff. Nice thing about dot product, the order doesn't matter. You could do u dot v, v dot u. You end up with the exact same answers, just for the record. C, remember, is a scalar. If they throw a scalar in there, you could do the scalar to u first. You could do the dot product. You can do it however you want. You will end up with the same exact answer. Now, just to show you that these work, we're not going to prove every single one, okay? But let's just look at the fourth one. If you did u dot u, well, just to make it easy on us, let's just write out what vector u is. So I'm just using A1, A2 for the horizontal component, vertical component. You can call them whatever. So I want to do u dot u. So sometimes it helps just to write it the second time so you have it in front of you. So if I'm doing the dot product of those, which looks weird, the same 2 vectors, same deal though. You're going to multiply the horizontal components. Well, I'm not going to write A1 times A1. I'm just going to put A1 squared. And then I'm going to multiply the vertical components. Well, I'm not going to write A2, A2. Let's just go squared. So looks crazy. Now, to show you that that is the same thing, let's see. Do we remember what these vertical bars mean? Magnitude, the length. Good call there, Grayson. I was happy nobody said absolute value. Okay, good call. Now, magnitude. We did that. When did I see you last? Wednesday? I'm losing track of days. We did magnitude on Wednesday. Notice there's magnitude in those formulas also coming up. So let's just review how to calculate magnitude. Remember, it is the square root. And of course, we're going to square the first component, that Pythagorean theorem, and the second one. Now, that's just the magnitude. They have the squared on it. Well, what happens when you square a square root? Okay, assholes. So you do end up with the same thing. So u dot u does turn out to be the same thing as your magnitude squared. I'm not going to prove all 4 of those. I just thought we'd prove one that actually really works. So we don't just think some weird old math guy made up these formulas to torture kids. I do. Actually, there is proofs they work. All right. Just like that, page 1 done. See, we're cruising. 4 to go. Okay. Now, again, this is all crazy wordy. And really, notice on your formula sheet, look at your formula sheet close. I do not have both of these formulas on there, okay? Don't be like, oh my gosh, I have to memorize one. No. We're really going to be using the bottom one, which is the one that's on your sheet. We're going to be looking at trying to find the angle, and you can see in the lovely picture here, theta. We're going to be trying to find the angle in between the vectors. Well, you can do that with the dot product theorem, okay? So the dot product theorem leads to the bottom one, which is the one we're really going to use. So if you do the dot product, magnitude of vector u times the magnitude of vector v times the cos of theta. Those are equivalent. The dot product equals the product of the magnitudes and the cos. Well, we're going to be after the angle. So all this bottom equation is manipulating this one. They just went through and solved it for cos of theta. They divided those magnitudes off. This is the one that I have over here on the sideboard, and that's the one that's on your formula sheet. So that's the one we're going to use when we need the angle between the vectors, which is the next thing we're going to work on. Okay, find the angle between the vectors. So you are basically just, I'm using the formula. First thing in the formula, of course, is the dot product. So let's calculate the dot product. So horizontals first, 2 times 4. And then I'm going to do the verticals, 5 times negative 3. So this is easy, but it's a lot of calculation. So when I'm looking at my angle, now I also want to know, so I got the top, I got the numerator. I want to know the magnitude of u. All right, I'm going to calculate that next. Magnitude of v, and then we'll try to get our angle. Well, let's just do all the calculations here. Magnitude of u, square root, 2 squared, 4, 5 squared, 25. And you will see too, it will say on your quiz, of course, next week to leave your answers in simplified radical form that doesn't want to miss decimals. So I'm just going to leave it root 29.
Will it say simplified?
Yep, sure does. That's for you, Avery. All right, magnitude of e. So we're going to have 4 squared plus negative 3 squared, or 16 plus 9. Well, 16 plus 9, 25. That comes out nice. What's the square root of 25? 5. Now, to get our angle. So I've got all the calculations for the formula. I'm almost there to get the angle. So cos of theta. So remember, it's the dot product, which we already got that, negative 7, over the magnitude of u times the magnitude of v. And also, I hate when they just assume you're going to know things. Just for the record, I will have a little note on here on your quiz or whatever. It's going to want the degrees, the angle in degrees. So check the calculator mode. Check it. Make sure you're in degrees. I'm going to pull up my calculator too. Now here's the thing, people. Is like square root of 29 or 5 on your unit circle anywhere? Is square root of 29 on the unit circle anywhere? No. So the unit circle is not going to help me. So that's why I said calculator. I'm going to do it in my calculator. We know to get an angle, I'm not just going to hit cos. I'm going to do second cos, cos inverse. And I'm going to type in that crazy looking blue fraction. Negative 7 divided. Now, I get a little paranoid about order of operations, of course, here. I'm going to put parentheses around the bottom just to make sure it doesn't mess up anything. Because I trust nothing. And then times 5. You could have wrote it 5 square roots of 29 to make your life easier, too. Doesn't say what to round to. I'm going to go 105.1 and call it good. So be careful how you type it in, of course. I use parentheses around the bottom just to make sure it didn't mess up order of operations. Don't forget, too, you can use that alpha y equal if you want to pull up that horizontal fraction bar to make sure you don't mistype anything in. So I would say a little time consuming, but nothing too horrible. A lot of calculations, you get the formula. You can't really beat it. Any questions on the angle? All right, next thing's easy. 2, I think so far nothing too crazy. So one of the new vocab words you're going to hear this chapter, they're going to talk about orthogonal vectors. Please be quiet, guys. So orthogonal vectors, and you will see that, of course, instead of the word perpendicular. So I'm going to be asking you, are the vectors orthogonal? Which really means perpendicular. Well, super easy. Remember, this means dot product. If you get 0, they're orthogonal. If you do not get 0, they are not orthogonal. All right, let's do the dot product and check it. So again, I'm going to do the horizontal first, 3 times 2. Then I'm going to do the vertical, 5 times 9. Well, I don't feel good about this.
I don't think it's 0.
Is that going to be orthogonal? No, we didn't get 0. Why keep going? We know it's not 0. Wrap it up.
I'm gonna guess this one is.
Am I getting predictable in my old age? Oh my God, that scared me. I wasn't ready for that. Okay, 2 times -1. 1 times 2. How's this one looking?
Yeah.
Yeah, we got 0. So yes, they are perpendicular or orthogonal. And just like that, page 2, done.
Not even halfway.
But come on, come on. All right, we are, I know, as we work down our formula list, now we're kind of working on this purple one. So the component of V along U, that's our next one up there, next formula we're going to talk about. But again, you'll get the formula on the sheet, obviously. You just have to do the calculations. So, the component of U along V. Now, of course, you know, math, we have to have, are we under control? Of course, in math, we have to have like 5 different words to represent the same thing. Of course, sometimes you will hear it, I've seen it used a lot, the scalar projection of U onto V, so I just threw that on there. Of course, just to keep it consistent with your formula sheet, I'm going to use that component of U along V to make it easy for you. So, to define that, of course, you've got your magnitude of U. So remember, that's the length times, I'm not going to put a time symbol in, the cos of theta. So if you look at the picture, the component of U along V, that's what we're going to be calculating here in a minute, is the magnitude, the length of the portion of U that points in the direction of V. So this little red piece is technically what we're finding, just for the record, and we're going to do it with that formula. So here is a very lovely picture, a real world application of such a thing. So a car weighing 3,000 pounds parked on a driveway that is inclined 15 degrees to the horizontal is shown in the picture. Okay, that's exciting. A, find the magnitude of the force required to prevent the car from rolling down the driveway. Well, remember, magnitude. So I'm going to draw my magnitude bars here. Now, first I'm looking at this and I'm like, which vector are we talking about over there? Are we talking about U, V? What are we talking about? W. So find the vector. I got to read this again. Find the magnitude of the force required to prevent it from rolling down the driveway. So I'm like, oh. So down the driveway. So if it's rolling backwards or down the driveway, what I'm really looking at is what angle am I using? The 15 or a 75. Well, if the car starts rolling back down the driveway, I'm looking at that 75 degrees. So we're going to do, of course, the magnitude here of U. And we've got our 3,000 pounds. And remember, cosine, that's a very sloppy 0. Because we're going horizontal. We're not going up and down. We're talking about the horizontal. That's 75 degrees. Now, here's the thing. 75, not on your unit circle. This is why I said you need your calculators today. So I'm going to really just straight type that in. 3,000. Do I have too many zeros up? I'm okay. So 75. So I'm going to round that. It doesn't say a tarantula. Let's just go to the whole unit. I'm going to do 776. Now remember, we're talking about forces, which in physics, we're talking about pounds. Now, find the magnitude of the force. I feel like I'm teaching physics today. Experienced to the driveway due to the weight of the car. So, this time, of course, really what's going to change is your angle. So, find the magnitude of the force experienced by the driveway. Well, I'm looking at the driveway, and of course I'm after what's the angle with the driveway? 15. And again, 15, obviously not on our unit circle, so I'm just going to type that straight into the calculator. So let's see what we get, 30,000. I think I missed a 0 here writing that. 30,000 cos 15. 3 cos 15. Okay, so let's round it to the whole. Let's go 2898 for it, since we rounded the other one to the whole. Got it. Got it. Okay. All right, so any questions? We're going to do some more with forces here towards the end. Elliot.
Why is the force to prevent the car from rolling down, but why is it 75?
Because you're talking about the force going straight down, pulling it down like gravity. So you're looking at this 75-degree angle, how it's pulling it down. It's a physics problem.
Oh, so it's the angle that the driveway is with the line straight down,
Yes.
which is the line of gravity.
Yep. Yep.
I see.
All right, so you've got the formula on your sheet, on the bottom of your notes. Flip the page. We're going to use our formula.
We're over half.
I know, we're cruising right along, people. And really the last page isn't too bad. So let u be that vector v. Find the component u along v. So no magic here. You're using this purple formula. We're just going to start calculating. So first up I need is the dot product. All right, well we can do dot product. U dot v. So 1 times negative 2. Got it. 4 times 1. So easy peasy, we got that. Now, next up, of course, we need, I'm looking at the bottom there, we need our, I don't know what's going on in the hall, magnitude of V. So easy calculations, but you have to kind of remember how to do all these. Remember, this magnitude one is not on your sheet. That's what we did Wednesday. That should be easy. We should know that one. And of course, that's that Pythagorean theorem. Make sure you do V. So negative 2 squared, 1 squared. Okay. And then to do my final answer, of course, it's just the quotient. I'm just going to divide those two answers. And I might have to do a little simplifying, of course. So I'm going to put my answer, and then of course you've got the VU. So the dot product on top, magnitude of V on the bottom, and last but not least, we should always rationalize our denominator. So I'm going to make it 2 root 5 over 5. So that would be the length, kind of crazy stuff here. That would be like the length if you were calculating it out of course, you can see here the picture of the U points in direction of V. All right, that's all you're calculating there. One more slide. Now, next formula, I guess that's kind of pink colored, is kind of this pink colored one we're going to do. So the projection of it, if you look at the directions and the pictures and stuff, it's very similar to what we just calculated on the purple formula, but the difference is this actually turns out to be a vector. It's going to be in component vector form when we're all said and done with it. A lot of similar calculations. Dot product, we can do it. Magnitude, notice squared, we got it. And then this is just going to turn out to be a value, kind of like that 2 root 5 over 5, that you are going to multiply to your vector. So the difference is they're very similar, it's just the style of answers. This is giving you just the length, this is going to give it as a vector style answer, okay? And we'll talk about this resolved into U1, all that shenanigans in a minute. But let's start with this. Find the projection of U onto V. Okay, so pink formula, let's do it. Let's start with the dot product. So and I'm going to do 9 times 2. So of course we're just going to add those together, 20. So I'm working on the denominator, the magnitude of V squared. Well, the magnitude of V, negative 1 squared, 2 squared. This seems dumb to write this because you're squaring it. Really what happens to the square and the square root? Yeah, they go away. So we end up just with 5. Bless you. Okay, so we've got our denominator right now. So just to kind of set it up, here's where we're at. Let me back up to the sheet here. So we're going to have 20 over 5 which I'm gonna write that, but really, what's 20 over 5?
Or,
So I'm gonna make that a 4, and you're gonna multiply, it's like a scalar. You're gonna multiply 4 through vector v, and that is going to be your final answer. So let's write it out pretty here. So we got 20 over 5 times vector v. I'm gonna make that a 4. So that is like a scalar. So the only really difference is this time we're putting our answer in a vector style answer. So I'm going to run 4 through v, so negative 4, 8. So that's really, it's very similar. If you look at the pictures, you're referencing the same thing. Just this is giving you the length of it. This is giving you the answer in a vector style. But you get all the formulas. Okay. All right, this is the thing we got to talk about. Let me go back to the formula. So this is on your sheet of course 2. This is the next thing they want you to do. Obviously, it's on your sheet. It's pretty easy. You just got to follow the formula. If the vector v is resolved, sounds fancy, into u1 and u2, where u1 is parallel to v, u2's perpendicular, orthogonal, then of course, here's your calculations. So just to practice or to show you how to do this, that's that part B. We're going to resolve it. So first, u1's the projection. Well, I just figured that out. That was that, was it negative 4, 8? Yeah, negative 4, 8. So I'm going to start with that. u1. We just found that. So I just literally copied it down. Now, if you look back at your formula, u2, we need that. So u2 is u minus our projection. So u2, let me get to it here. u2 is our u vector minus this guy. Okay, well you've got the u vector, and you can see, so I'm not clicking it back and forth. Remember, u is negative 2, 9. So I'm just putting that in for you. And of course, I'm going to do the math there. I'm going to add or subtract, of course, your horizontal pieces, and I'm going to do the vertical ones. So negative 2 minus negative 4, 9 minus 8. Okay. And again, that's all on your formula sheet, but just so we know what we're actually calculating, we're doing this craziness. We're making one where it's parallel to v, and then we're making it a vector that's perpendicular to it. That's what you're working on. We made a parallel vector, then we made a perpendicular vector. That's all those little calculations. Remember, you always get the formula sheet. Easy stuff. All right, last thing we have to do, I feel like, again, I'm teaching physics today. We have to talk about work. Okay, all right, physics, right, work, we got it. So, work, the use of the dot product, we're going to use that. And remember, this in the formula means dot product. We're going to be doing dot product. In physics, work is the energy transferred to an object by the application of force along a displacement, direction, okay? In the simplest form, a constant force aligned with the direction of motion is the product of the force and the distance traveled. So we're going to do the force times the distance. Dot product with the distance is really what we're after here. Word problems. Here we go. Are we on the last page already? Look at that. Look at that. Okay, force is given by, there's your force vector, and the object moves the point from 1, 3 to 5, 9. Now, notation is important. Notice on that 1, 3, and 5, 9, those are parentheses. Those are not in vector style. I need it in vector style. Because remember, the D in our formula is, of course, the direction. Well, vector is a direction. So from 1 to 5, a little mental math there, 1 to 5, and then 3 to 9. Put a D on that. So, nice and easy, our little work formula, remember, is the force dot D. Well, they gave you the force. We just figured out the direction, the displacement vector. And I'm just going to do the dot product of this stuff. So I'm going to have 8 plus 18, total it up, 26. Now, we should label that. So force, remember, when we're talking about force, you're moving something. So, and usually in force, unless they tell you something weirdo, they're doing some different, like metric scaling or whatever, you're looking at foot-pounds.
Foot-pounds?
Mm-hmm. Feet per pound. We're getting sciencey today.
Are you gonna take points off of me on foot pounds?
Probably on yours I will, Owen. Just kidding. Just kidding.
I would too.
No, and usually like I'll have like in the directions like I'll have like foot per pound or whatever like label. Oh yeah.
Is that foot pound?
Foot dash pound. Foot pounds. Yep, foot pounds. We're getting sciencey. Alright, I like this little guy, he's towing the wagon. Alright, a man pulls a wagon horizontally. Here you go. This is a little better, people, quiet, paying attention. This is a little bit better one to show you with the foot and the pounds and all that sort of stuff. So a force of 20 pounds on the handle. So he's pulling the wagon, he's got a 20-pound force on the handle. Handle, you can see, makes a 60-degree angle with the horizontal. Find the work done and moving the wagon 100 feet. So 100 feet for your distance, 20 pounds of force. That's that foot-pound label that we're really going to look at. All right, let's get into it. Here we go. So, well, I don't know. I feel like I should write down the formula, right? Our force times D. So that's, of course, what we're working on. Now, let's first talk about, we have to talk about the force here. We're going to start with that one. So, of course, your force of the handle. So it says he's exerting 20 pounds on it. Well, we want that, of course, in a vector style. So we have to do our 20 times the cos of 60 and our 20 times the sine of 60. So our horizontal component, now that's 60's on my unit circle, we'll do it in a sec, and then I'm going to do 20 sine of 60. So let's start with that guy. All right, 60 degrees, that's nice, it's on your unit circle. What's cos of 60? I heard it. What's sine of 60? We're 3 over 2, I heard it. Okay, and then we're just going to simplify this here a little bit. So obviously we're going to have 10, and I'm going to make this 10 root 3. Now, we need the D, of course, the next one. Ready for that? Now, I like this guy. Now, remember, this is your distance, okay? This is your displacement. You're moving the wagon. Well, here's the nice thing about this one. If he's moving the wagon, I'm towing the wagon. Are you moving, and that was very nice. Are you moving horizontally, vertically, or both? If I'm towing the wagon. I'm just going horizontal. There's no vertical. So I know my vertical component, 0. What's the horizontal component? How far is he moving the little wagon? 100 feet. So all I have left to do is the dot product. Yeah, I just got to multiply this and add them up. So I'm going to have my horizontal. Well, what's 10 times 100? 1,000. I don't even know where I really am writing this. 10 square roots of 3 times 0. And of course our foot pounds. I love it. So again, this is a better example with him, with his wagon with his 20 pounds of force on the handle and he's moving it 100 feet. Must be a lot of stuff in that wagon. Yeah. So any questions on that guy? No. All right. So lots of formulas.